Good morning. Good morning. Can everybody hear me? Hopefully.
Yeah, I'm able to hear you.
Thank you, Ryan. Thank you. Excellent. Good. So, uh, who remembers where we left off last time? I've been going over stuff, but I forget exactly where we were. Did we talk about the mercurous chloride, KSP? I think so. And yeah, I think we talked about some of these issues where,
I think it was past this slide, at least. I don't know. Just keep
yeah,
scrolling through them, and I'll tell you whether or not I recognize it.
excellent, excellent. So
All right.
solubility product here, solubility product of the options, um, then common ion effect.
Yeah, we saw that.
Okay, and the problem, and there's this interesting problem if you add concentrated HCl to saturated KCl. Not sure if we did that one. And then this guy. I think here, let's pick up here. I think because I'm not sure we did
Yeah,
these.
I don't recognize this slide or the next one, so I'm pretty sure this is our stop.
Excellent. Thank you so much. Thank you. Thank you. Okay. So, a demonstration, so to speak, of the common ion effect here would be an experiment where you add HCl, which is actually more soluble than potassium chloride. You add HCl to KCl, and uh, and then if you add it at too dilute a concentration, you get no precipitation. But if you add it at a sufficiently high concentration, then the additional chloride from HCl will trigger precipitation of KCl. And I just have a little blurb on that worked out for y'all. Oh, and by the way, I'm not feeling super hot today. I mean, it's not like COVID bad or anything. I'm just not feeling my best. So I'm probably not going to be like writing a lot on screen. I'll just use the notes that I've generated. Sorry about that. I'm just sort of. So anyway, but the KSP for potassium chloride is about 13.7. Right? That means that the product of those ion concentrations never exceeds 13.7 in solution. Right. So if you take 3.7, that is molar, that is saturated KCl in water, and at an equal volume either 6 or 12 molar HCl, then what will happen is after you do the dilution calculation, see, well, the potassium part is going to be diluted by a half. Then you have to do two different calculations for the chloride, actually three here. One is the chloride from the original, 3.7 molar chloride. Two is the chloride from the 12 molar or the 6 molar chloride. And the 12 molar chloride will add 6 molar to the test tube. When you add that to the original 1.85, what you get is 7.85, right? Multiply that by 1.85. Then you get a reaction quotient, Q, that is equal to 14.5. So 14.5 is greater than KSP. And you'll recall that KSP is 13.7, and KSP is the concentration product of these two ions in a solution in a water solution above those ions, water in this case, right? So in this theoretical calculation, we're looking for this addition of HCl, which will increase the Q value for KCl above the KSP, right? And in the case of 12 molar, adding 12 molar HCl, it does exceed KSP. And in the case of adding 6 molar HCl, it does not exceed KSP. So these are two cases, and this is illustrative of the common ion effect. So if you add the 12 molar HCl, you'll get some precipitate, and we can actually calculate how much. Although we don't actually need to do that right now. So the next subject we can delve into then is the idea of separating chemicals by precipitation. And here's an example of the separation of lead from mercury. If you have a solution, for example, that is a combination of lead iodide and mercurous iodide, you can tell here that while they're both insoluble, they're both neither of these is significantly soluble in water. The mercurous iodide is far, far less soluble, right? And so the question is, can you separate these two, lead and mercury, by adding iodide? And moreover, what we want to say is, can you lower the concentration of mercury by 99.99% by selectively precipitating it with iodide? So, and at the same time, leave all the lead in solution. So this is, I would actually be a little bit scared about doing this in practice, because my mind would tell me about the kinetics of this process, where where you add, this is probably adding potassium iodide to lead nitrate and mercurous nitrate. And then when you add the potassium iodide, you get this precipitate, right? And I think that the precipitate probably contains lead and mercury, because at the moment that it hits the solution, that boundary layer is going to have high concentrations of iodide, and it'll exceed both of these KSPs, right? However, if there is dynamic dissolution and redeposition, that is, if there's a bona fide equilibrium between these solids and this solution, then in theory, we might be able to separate these ions using iodide. So let's see how that works out, right? So I'm going to go to my notes here, and hopefully it will be clearer. I'm not really sure. So let me just check back up here. Okay. Looks like I did it using 10 to the minus 4 molar mercury and lead ions instead of 10 to the minus 2, but that's okay. So what I'm setting up here is that we're starting with mercurous nitrate and lead nitrate, right? And the KSPs that we're dealing with are Hg2 plus 2I minus makes Hg2I2. And Hg2 is a bona fide thing. It's funny, there's mercury and iodine. They both exist as these funny complex ions in solution. But Hg2I2 forms, and the KSP for that is 4 times 10 minus 29. Lead iodide forms 7.9 times 10 minus 9, right? And we want the mercurous ion to be around 10 to the minus 6 molar, right? So what that would mean here is that the iodide would be, we can substitute in the iodide concentration that would suppress this 10 to the minus 6 molar, right? And that iodide concentration, if we solve for it in KSP, comes out to 6.8 times 10 to the minus 12 molar. So herein lies a significant rub. How can you get iodide up to 6.8 times 10 to the minus 12 molar? Well, the way to do that would be to add exactly the same amount of iodine as you have mercury in the solution, and then add another tiny spike that brought it up to 6.8 times 10 to the minus 12 molar. And that would do it, right? So while this is doable, it's not easy to adjust it by such fine amounts. So how would this affect the lead iodide? Well, you can compute the Q value here for lead, right? We got 0.01 for the lead, and then 6.8 times 10 to the minus 12 for this. And that comes out to 4.6 times 10 to the minus 25, which is 10,000 times, oops, oh God, I screwed this up, didn't I? Which is way, way smaller than the KSP, 7.9 times 10 to the minus 9, that's supposed to be. This is it's much, much smaller than the Q value for lead iodide, right? So lead iodide would not precipitate at that point. However, it would be helpful at that point to see how much more iodide would actually cause lead to precipitate. So this is theoretically possible because by precipitating the mercurous ion and bringing the mercurous ion down to 10 to the minus 6 molar, you can leave all the lead ion in solution. But it might be tricky, especially right around that inflection point where you're adding where you've just precipitated all the mercurous ion and then you'll start to precipitate lead. So that would be an exact separation, where you take the 1 and the 2 and you exactly separate them. A lot of times what you would do is you would under titrate, and that way you would leave some mercury in solution and you'd collect the mercury, or you'd over titrate and leave some lead in solution and collect the lead, right? Or leave some lead in the solid and then collect the lead in the aqueous phase. So it's a little bit subtle there, but But in theory, it can be done. I think that's the point that Harris is trying to make here. So, so this is basically the answer there. And then Isaac Kolthoff, the theory guides, an experiment decides. So this is the point of like, okay, in theory it's possible, but in practice maybe not.
Sorry to interrupt, but I don't know if you saw in the chat, but somebody want to know if you could update the lectures chapter 6. Like, I'm assuming the slides.
Absolutely. Thank you, Ryan. Thank you. Yes, I just opened the chat, so I will. Yes, I will update those. Thank you. It's funny. It's probably my own damn fault, but it's a little bit. It's a little bit different to have such a one-sided sort of lecture, Oh my gosh, our attendance is plummeting. Oh my God. Oh geez. I hope everybody's hanging on there. Can I ask, is the homework super onerous for you guys, or what's, or just the lectures are super boring, or what's going on? I mean, you guys are here, so
This is just early morning, I guess, and then like sometimes the homework is can get I don't know, just repetitive sometimes when like some of the questions are it's just like a rewording of the questions sometimes. But I don't know about this homework.
Yeah,
I haven't gone all the way through, but for some of the other ones, like it just like seems like repeat questions. But it was actually pretty good for the last chapter though.
Okay. All right. What do you say, Alvin?
I was saying the same.
Okay. All right.
It just depends what kind of week you're having with the other classes too.
Everybody's having a crappy week. I would be fine today. I would be totally fine. But I actually started the 6B homework last night so that I could sort of, assign it and strike a few questions. And I got the first question wrong. And it took me an entire page of calculations. And I could not figure it out. And I was so freaked. I was so freaked, right? Now, here's what happened. I was so freaked out. And then I got really hungry. And I went to I was actually in the lab. I went to La Victoria's and I ordered a quesadilla, 2 super tacos, and an horchata. And I ate the whole damn thing. And that did me some damage. I'm too old for that. And then, I came home. I was still depressed because I couldn't figure this stupid question out. I mean, I did figure it out in a way, but I guess it's not right. And then I ate a bunch of ice cream last night. I was watching TV, and oh no, I just feel terrible this morning. I abused my body. Anyhow, so this is not your fault. This is not your problem. I'm just sharing here my stupid life. Okay, so let's talk about complex formation. So lead iodide is an excellent example. Lead it's a funny ion though, because it's way off to the right. It's under carbon. And so lead iodide, I don't know if this is probably common to all the transition metals. So lead ion is a Lewis acid, which means that it has, basically it has all these open orbitals. Oh, total assignments, we're going to keep them up. We have to keep them up until the end. We'll probably have another 3 more lecture assignments, 3 more homework assignments, because we're like literally half as far as a normal Chem 55 class is going. I mean, I feel guilty I'm somehow underserving you, but it feels like we're just moving through a lot of things that are actually important, you know? I just don't, I don't know how to throw out entire chapters. But yeah, we're gonna have a homework every semester or every week. right through the last week, I think. So, but anyway, these metal ions, they have a bunch of empty antibonding orbitals and D-type bonding orbitals. They're just empty, right? And they can accept lone pairs from halides and other these are called ligands, right? And so what can happen then is that if you're precipitating PbI2, right, you can take at low iodine concentration, you can predict the amount of iodine that's going to or the amount of lead that will be in solution as you keep adding iodine, right? And this line does not hold. But it turns out that there's a really gosh darn clever way to account for the observation, which is that as the iodide concentration goes way up, excuse me, you form complex ions. So this is all Pb+2 and PbI2 solid, right? This is a small amount of PbI that forms. This completely horizontal line here is PbI2 aqueous. Now this is solid this is horizontal because it doesn't care what anything else is in solution. It's just equilibrium with the solid. This is PbI3, this is PbI4, right? And if you add up all these, you can do an equilibrium calculation. You get damn close to the observation, right? And here's the math behind all that. Here's the KSP. PbI2 makes Pb2 plus 2i minus, right? And this is 7.9 times 10 minus 9. We saw that in the mercury-lead separation. But there is the formation of Pb2 plus I minus makes PbI. And there's KSP, and this is called K1, right? And this is the addition of one ligand, right? So that's why it's called K1, right? And that's the equilibrium expression is PbI plus divided by Pb2 plus times I minus, right? Divided by everything in the denominator there. And that's KSP in there is 100, right? So this is highly favored, right? To form this. And then you can define what are called cumulative formation constants, which are the beta values. And the beta values, one of the part of the magic here is these all start with Pb+2. And you can show how this forms PbI2 aqueous. Okay. And then Pb+2 plus 3i minus makes PbI3. They're all aqueous, right? All these ions are aqueous, right? It's just that there's two forms of PbI2. There's a solid, and then there's this dissolving molecule, this dissolved PbI2 molecule, right? And there are beta values for all these. There are beta or equilibrium constant values for all these transformations. They all involve Pb+2, right? And iodine only. So there's so many equilibrium constants you could write for this system. You could write this, plus one iodide makes I3, I3 plus one iodide makes I4. There's a whole bunch. And somehow this holds together in an algebraic superstructure, right? And you can, you can define the total dissolved iodine. That's these 5 species here: Pb plus 2, Pbi plus, Pbi2, Pbi3 minus, Pbi4 minus 2, right? Then you could come across a question as finding the concentrations of Pbi, Pbi2, Pbi3, etc. in a solution saturated with Pbi2 and with some dissolved iodine, right? And the dissolved iodine is in this low concentration and this relatively high concentration, right? So there's 2 sets of equations here. So let me go over those. Oops, in my notes. Yeah. So there's KSP, right? That's PBI2 makes PB plus 2 plus 2I minus. Then PB plus 2 plus I minus makes PBI plus this weird thing. That's governed by K1, right? And that's 10 to the 2. It has this equilibrium expression. There's beta 2, PB plus 2 plus 2I minus. Right? There's a K governing it. Or this is actually beta 2 here. This should be K1, beta 2, beta 3, beta 4. I just made a mistake there when I wrote the notes. But and these are all the beta values, right? That govern this, right? So the question is, we would like to account for all these concentrations when we have different lead ion concentrations in solution. So the first thing we want to do is we want to say, well, let's take the KSP, right? And we're going to solve that for the lead ion concentration. And this comes out to 7.9 times 10 to the minus 9th molar, right? Actually, I misspoke earlier. It's different iodide concentrations, right? So there's lead ion concentration from the KSP, right? You may ask, well, how can I do that, right? How can you solve for lead if there's so many equations for lead? And the reason I can do it, at least as far as I know, is that all of these equations are simultaneously true, right? So the PB plus 2 concentration is governed by KSP. It's also governed by all these other equilibria, right? But they're all true all the time. So I hope I'm not overstating this, but this is my understanding. PBI plus, then, this first species will be its formation constant times, this is the denominator, right? We know PB plus 2 in the KSP. We know I minus, and we know the formation constant is 100 here. Right? Is that right? Yeah, 1.0 times 10 to the 2, that's K1. So this value here is K1. And so this means that the PBI plus concentration will be this amount in molar. Right? And we can do the same trick with all the remaining concentrations. Here's PBI2. And this is just a rearrangement of the equation, the equilibrium expression for PBI2 aqueous as a function of PB plus 2 and I minus, right? So if I come up here and I want to solve this for the PBI2, then what I would do is I would say, well, I would solve for this, and it's going to be equal to this times this times this, right? So this over this times this equals this. Therefore, this is equal to this times this, right? This is equal to PB plus 2 times I minus times 1.4 10 to the third. Oops, that's hard to read there. One point 4 times 10 to the third power, right? So this is just solving that equation for PBI2. And that's what I did down here. Oops, is this focused? There we go. That's actually a little bit better now. So there's PBI2, and it's just equal to the product of those concentrations. That comes out to, there's actually two answers, one for 10 to the minus 3 molar iodide. This guy here, these are the two options for iodide concentrations. And then we get two different, oops, I only calculated one of them, it looks like. But this one is 10 to the minus 5, and the other one is, the other one is 1.106 times 10 to the minus 6. And then if we come to PBI3 over here, then we can go through them and we'll get 7.9 times 10 to the minus 9 and 6.5 times 10 to the minus 5. Similarly with a PBI4, now here there's a huge difference between these two. This is sort of growing, right? This one is growing and this one's shrinking, right? This comes out minus 5 and minus 9. This is minus 4 and minus 10. So this goes 7, 6, 5, 4. This one goes 4, 5, minus 5, minus 9, and minus 10. So it's this exponent up here that drives these changes. So in any case, this is how you would solve this. And apparently, this is all true. Although I have not personally witnessed this type of transformation. So then this is, this is their incarnation of this, right? And we can, you could do this at some point, right? It's just exactly how I did it, right? Now, this is probably suitable for today. There's a good discussion of the general qualities of acids and bases, and I'd like to go over them with you today. And it looks like I'm not going to get through as much in class today, so I may have to postpone the planned completion of chapter 6 until like maybe end of next week. So let's try to get homework 6A done for the end of this week, then homework 6B maybe end of next week. Excuse me. So protic acids and bases, these are kind of the easy type. There's just in terms of their impact on the H3O plus concentration in water, So, an acid increases it, a base decreases it, and and then also H3O plus and OH minus are they're locked together, right, in this equilibrium. And, there's a definition of protic, meaning involving the transfer of a proton from one molecule to another. You can call it a solvent protic if it has a labile that is a transferable H+, right? And in the Bronsted-Lowry definition of acid, acid is a proton donor and a base is a proton acceptor. So HCl is the acid in this case. Water is the base, right? So that makes hydronium and chloride, right? Now, hydronium is the quintessential acid in water. And it's what we call, when we write left bracket H plus right bracket, and we're talking about water, that means H3O plus, right? And then HCl gas plus ammonia gas makes ammonium chloride. It can be solid, actually, it can be gas too. And these two guys, this is the acid, this is the base, right? This donates, that accepts, and then this is the salt, which is the product ammonium chloride. It can be solid or aqueous or whatever, right? And then a strong electrolyte dissociates nearly completely into ions in dilute aqueous solution. So have ammonium chloride makes ammonium and chloride. So other examples of conjugate acid-base pairs are acetic acid and acetate. This is they just differ by the addition or subtraction of a proton. The acid has the proton, the acetate does not have the proton. This can accept a proton and go that way, this can donate a proton and go that way. Then methylamine and methylammonium, right? So amines are, carboxylates and amines are the way that students get tripped up in Chem 55. It's because we're used to strong acids like HCl, HBr, HNO3, H2SO4, etc. And what we're working with mainly in Chem 55 are weak acids. So acetic acid is a weak acid. Methylamine is a weak base. And they react via certain equilibrium to make acetate ion and methyl ammonium ion, right? So this is an acid and its conjugate base. This is a base and its conjugate acid. You can write this reaction in reverse and it would still be correct. However, the arrow to the right is larger than the arrow to the left. So if you want to talk about the nature of the proton in the hydroxyl group, the simplest formula is H3O plus. And this is one way to express it. There's and it's called hydronium, and hydronium perchlorate, or hydrous perchloric acid is really hydronium perchlorate, right? And then in water, hydronium itself is normally complexed by 4 other water molecules, right? So this is, water, acid will affect the surface tension of water, et cetera. It'll affect the physical properties of water because of these types of effects here. And, there's other potential structures for water, right? This is H3O plus, right? This is H3O plus dot H2O. And then, water can be a proton donor, and it can be a proton acceptor, right? So water itself can act as an acid or a base, depending on the strength of the acid or base it's dealing with, right? So water plus methoxide makes hydroxide and methanol, and water plus hydrogen bromide makes hydronium bromide. And this is just a weird one. I don't even want to talk about this. So I'll scratch that out later. But water undergoes autoprotolysis, and all protic solvents undergo autoprotolysis to some extent, right? This is probably not prevalent, right? But two waters can make a hydronium and a hydroxide, or you could say that one water makes hydronium and hydroxide. These are equivalent in the equilibrium terms because water is defined as unit concentration for everything that we're doing. And everything I've ever done, basically. So there's autoprotolysis of water, and then other protic solvents, like this is acetic acid. And I was surprised to find that it's a liquid. You can get acetic acid with no water, and it has a tiny amount of autoprotolysis. I don't know the constant. I don't know if anybody knows the constant. It's pretty darn small, though, right? So the presence of these ions can be detected in water by the conductivity of water. And pH here, worth mentioning, it's simply a logarithmic scale to measure the H plus ion concentration in water, right? And so pH goes from, it can take on pretty much any value, right? But practically speaking, it goes from 0 to 14. So let's see. 0 to 14 in practice. 0 is for 1 molar acid. And to 14, which is 10 to the minus 14th molar H plus. Oops, keyboard work. That's weird anyway. Oh well. 10 to the minus 14 molar H plus, right? Or 1 molar base, right? And the POH plus the pH is equal to the minus the log of Kw, which is 14.00 at 25C. So, you know, there's some temperature dependence on it, but we really are not going to work with this. It's just useful to know, you know, that below 100 degrees, you know, as water gets hotter here, it goes from, you know, basically just 14 here, and it gets a little bit more corrosive at higher temperatures here. So there's more H plus and OH minus in water at 100 degrees than there is in water at, say, 25 degrees. But don't worry about this. This is not to be concerned about, right? And the pH meter, which is a friggin' amazingly wonderful, life-saving instrument. It can measure H plus ion concentration from 4 to 10 pretty much right out of the box. You know, that's 6 orders of magnitude. And it's a cheap little guy. And it's you know, it's a brilliant thing, you know. So the pH scale is acidic at less than 7 and basic at greater than 7, and neutral at 7. So you can have pure water will have a pH of 7, and then also, you know, you can make buffers with pH of 7. So there's different ways to get there. All right. We'll do this one starting next time then, guys, and thank you for your attention. And please encourage other students to come to lecture and tell me what's wrong with my lecture that they're not coming. Okay, guys.
I have a question about like midterms. Do you think we're gonna have like one more or like 2 more before like the final?
Oh yeah, there's one more midterm.
Just one more? Okay.
Yeah, there's just one more midterm, and I'll put out an announcement about it today. I don't remember the exact date right now, but I think it's in like 2 or 3 weeks. So I'll put out an announcement about the midterm.
Oh yeah, I think you said it was on like November 12th or something.
Right.
Right. Yeah, I forgot about that.
Yeah. No problem. All righty. Good.
Thank you.
Have a good rest of your day.
All right. Thank you guys. Thanks. Thank you guys. Thanks.